So in general, if you have equations with very, very different magnitudes of numbers, then you start to get these round-off errors. Right? So we're going to look at this example where we have this a poorly scaled quadratic equation. So what we want to do is we want to find the roots of this quadratic equation. You have x squared, so the coefficient is 1. You have minus 54.32x plus 0.1. And so this b here is much larger than c. Now MATLAB could handle this. But if you're just doing this with a calculator and rounding to 2 or 3 sig figs, you could be running into a problem. So let's take a look at what this calculation would entail. So whenever you're doing the quadratic formula like this, you want to look at this second term here, which contains the discriminant, right? The discriminant being b squared minus 4ac. So what does this term here look like? You have the square root of negative 54.32 squared minus 4ac. So if I look at what these numbers turn out to be, then I have a big number and I have a small number. So the big number ends up being 2951 if I carry 4 sig figs, like the problem told me to do. And the small number ends up being 0.4 exactly. But if I'm only carrying 4 sig figs, then the small number here does not affect the big number at all at each step in the calculation, and therefore what's happening is the square root of this number ends up being approximately equal to 54.32, or just the opposite of b. So the minus 4ac didn't do anything to the b squared. Therefore, when I look at my root, if I solve for the plus root, I have x equals to the opposite of b, or 54.32, plus the second term ended up being 54.32 divided by 2a. Therefore, the plus root, which I'm going to call x plus equals to 54.32. Now it turns out that the real answer, if you carry more sig figs anyway, is 54.321816. So that's the real answer. So we have some round off error. No big deal, right? And in fact, if I calculate the relative error here, that relative error ends up being only, I'm not going to do the calculation, but it ends up being only 0.04%. So as far as normal calculations go in this class, or in most of your chemical engineering classes, this is a good approximation to the right answer. So carrying 4 sig figs is fine. However, when you solve for the other root of the problem, the minus root, you get x minus equals to the opposite of b again, so 54.32 minus 54.32 divided by 2, or x equals 0, or x minus equals 0. Now we know that's not the case, right? Because we know there was round-off error, and we know that because of our round-off error, we lost the super important part of the problem, which would tell us the difference between x minus equaling to 0 and x minus equaling to the real answer, being 0.001841. If I calculate the relative error here, then I have 100% error. And the problem was that I had two, quote, big numbers that were very, very close to each other, and I subtracted them. Or you could also say the problem was I had a big number and a small number, and I subtracted them. And then I lost the effect of the small number on the big number. That wouldn't have been the problem, except for later, then I subtracted off that same number, and I should have something left over, but I don't anymore because I rounded. So what's the solution to this problem? How do I fix this? How do I actually get what x minus is? I could carry more sig figs, but if I only have, let's say, instead of 4 sig figs, let's say this problem is bumping up against MATLAB's limit. And I don't want to do that. What you need to do instead of just saying, I'm going to carry more sig figs, is you need to reformulate the problem. So we want to reformulate the problem so I don't have this issue of having these two numbers, which should be very close to each other, being subtracted off from one another and getting 0. And so in the second part of the example, we're going to change the way the problem is formulated, and we're going to rescale the problem. Right? So the problem before was that I had b squared minus 4ac being much greater than 1. Sorry, b squared over 4ac. Because b squared over 4ac was roughly 10 to the 4th. 10 to the 4th power. Right? And so that made it so that the square root of the discriminant was approximately equal to b. Right? So we want to make the b's in the numerator cancel out. We can do that. So we can take our x minus being equal to the opposite of b minus the square root of b squared minus 4ac all over 2a. We can make the b's cancel out by multiplying by a form of 1, which is the opposite of b plus the square root of b squared minus 4ac, over, in the denominator, the same two terms, the opposite of b plus the square root of b squared minus 4ac. If we do this maneuver, then in the numerator we get b squared minus quantity b squared minus 4ac. And in the denominator we have 2a times the opposite of b plus the square root of b squared minus 4ac. So when we do this maneuver, then we relieve the problem of having the square root in the numerator, and then the b's squares cancel out. So I'm no longer subtracting off two numbers which are really close to each other. These numbers actually cancel out. And in the end, you get x minus equaling to 2c over the opposite of b plus the square root of yada yada yada. Which, if you reformulate it, ends up being c over a times the x plus root. So the b's just completely disappear from this formulation. And if you crunch out the numbers, that ends up giving you 0.001842, which is a relative error of 0.05%. So ultimately, we had a problem where the problem was ill-conditioned. It was badly scaled, just like we saw previously with matrices, where numbers were very different from one another, and subtracting them off gave you round-off errors. So in the same way, we have this badly scaled problem. But if we know how to work with these problems, we can rescale them so that they work better. And so that's part of the reason why we're in this class, to learn things like Newton's method when you have F0 and Fsolve, or to learn things like the Runge-Kutta method when, as we'll see next time, there are packages in MATLAB that will solve ODEs for you. Because if you don't know what's going on behind the scenes, if you run into problems like round-off errors, and MATLAB doesn't tell you about it, or even if MATLAB does tell you about it, you might not have, any way to know how to do anything about it, right? And so that's why we have to learn what are these issues that you could run into with numerical analysis, and how do you fix them.